Hello dear friends, welcome back. In this tutorial friends, we'll be looking at the integral. You can see I have here on screen, which is the integral of x raised to the power square root of x into the square root of the square root of x, and so on and so forth guys, all that over the natural log of x. So friends, it keeps on going forever. So friends, please watch the video from start to finish so you can understand all the concept associated with this particular integral. So friends, without further waste of time, let's dive straight into our video. Awesome. Alright, so friends, here's the question. You can see I have it on screen. That's the question. So friends, we want to evaluate this integral, but friends, as you can look at the integral so well, we see these three dots in here, right? Means it keeps on going forever and ever guys. So we are some kind of stuck guys. It looks similar to the problem I solved last time. It looks similar to the problem I once solved in this my channel. So friends, you only check that out, but we are going to use the same approach guys, the same approach. So we are going to try to investigate what this what the numerator of the exponent looks like. Okay, let's investigate it because it looks so cumbersome, since this three dots means that the function keeps on increasing. That is, this the square root of this square root of x guys keeps on going forever. So let's investigate that. Let's try to investigate this part that keeps on going forever. So guys, let's start with this square root of x. The square root of x out there guys means what guys? It means x raised to the power 1/2, right? So in essence, I want us to write all of the individual square roots of x as x raised to the power 1/2, and we just hope for the best guys. So this is now going to be x to the power 1/2 into the square root of x to the power 1/2. Like I said guys, all of these individual x's in the square root, we are going to write them as x raised to the power 1/2. Good. Then for example, as you can see, this first x is x raised to the power 1/2. That's good. Then the second is x raised to the power 1/2, right? But it is enclosed inside of what guys? Inside of one square root. So it is going to be what? X raised to the power 1/2 times what? X raised to the power 1/2, which is going to be x raised to the power what guys? 1/4. So we are now going to have x to the power 1/2 times x to the power what? 1/4, right? Good. Then friends, now this other square root, this other x raised to the power, this our x, this the second x raised to the power 1/2 is enclosed instead of what guys? Instead of two square roots, right? So it has to be x raised to the power what? 1/8. So we are now going to have x raised to the power 1/2, x to the power 1/4, then x raised to the power what guys? 1/8. Great. So friends, if we keep on doing the same process, repeating the same process guys, we are going to produce x to the power 1/2, x to the power 1/4, x to the power 1/8, up to we have x to the power 1/16, and this guy keeps on going forever. It keeps on going, friends. So at this point in time, friends, now we can say that this is just the same as x to the power 1/2, x to the power 1/4, x to the power 1/8, and so on and so forth guys. It keeps on going. Great. So friends, we should know that this our function part, this our infinite function parts, these guys, now we can try to say that since the bases are the same, right, indices can come in. Okay, indices can come in. We can further simplify it since they all have the same basis. Since the product of these are index numbers, as far as their bases are the same, we simply add their exponents. So we are therefore going to have x into x raised to the power 1/2 plus 1/4 plus 1/8 guys, and so on and so forth. This is because they both have the same basis. We can utilize our laws of indices. Great. At this point in time guys, we can therefore observe one important thing guys, that the sum of the powers of this our x guys can follow a geometric progression. Okay, this our sum guys can follow a geometric series, not just a progression. It's a series because we are summing all of the terms. Great. It can follow a geometric series. How do we know that guys? How do we know that that condition is true? How do we know it? Because we can write a formula for the sum of the first n terms, right? we can write it, but that's but if you want to show so well that it follows a geometric series, that therefore means that the quotient of the second term over the first has to be the same like that of the third over the second. Namely, guys, if we take 1/4 and divide by 1/2, we are going to have 1/2, right? If we take 1/8 divided by 1/4, we are going to have 1/2, and so on and so forth, guys. So there is a constant common ratio. So in this case, guys, we can move on to write the sum of the first n terms as a series as n goes from 1 to infinity of just 1/2 raised to the power n. Friends, this is true because if n becomes 1, we are going to have 1/2. N becomes 2, we have 1/4. N becomes 3, we have 1/8, and so on and so forth. In this case, guys, we can see that it's a geometric progression whose first term is 1/2, and whose common ratio r is still 1/2. Great. So in this case now, guys, since we have these 3 dots, which means we have to sum up everything we see, okay, because this plus then these 3 dots means we have to sum up all the terms. It is simply our sum to infinity, okay, that's the interpretation. Sum to infinity means we have to sum up all the terms beginning from when n is equal to 1 and when n is infinitive. And we know for sure that, guys, the formula for the sum to infinity of a geometric progression is simply given as a over 1 minus r, okay, s infinity equal to a over 1 minus r. But friends, I want you to draw your attention, because there are some cases where we will not be able to find the sum to infinity. That is when the series diverge, okay. But in this case, guys, this our series converge. Why does it converge? It converges because the absolute value of our common ratio is less than 1, okay. 1/2 is less than 1, right? Means it does what? Means it converges. Great. So if it converges now, we can compute the sum. We can find the sum to infinity by using the formula s infinity equal to a over 1 minus r. Plugging in everything, guys, we have our a to be 1/2, r to be 1/2. We are going to have s infinity equals to 1/2 over 1 minus 1/2. The denominator gives us 1/2. So in essence, guys, we are going to have our answer to be 1. Great. That is the answer that we have. This is what the sum of all these terms are going to amount to. They're going to just converge to 1. Good. That therefore means that, friends, these our terms, all these x to the power 1/2, x plus 1/4, and so on, guys. This our guy now is now just the same as x. This is the x here. Then sum of all of these our terms 1/2 plus 1/4 plus that has given us what? 1. So we have x to the power 1. Good. So in essence, guys, we have x to the power 1, right? Great. And this is just the same as our x, right? This is just the same as our x. Good. So summing all these terms, guys, it simply gives us x. It therefore means that this our original integral, guys, can simply amount to integral of x to the power sum of all of this stuff, guys, has given us what? Just x, right? X to the power 1. So we have x. All out of our, keep in mind that there was natural log of x, so we have natural log of x dx. Great. So friends, we need to evaluate this our integral. But friends, it looks so complicated, right? It looks very complicated because we have x raised to the power x over natural log of x, a very tough function raised to some power, raised to a very complicated power. So guys, there's more to it. But friends, there's still something that we must do, okay? There's something we can do. But before then, let us keep it in mind, okay? Let's have it in mind that we can express the x, this x in yellow. We can write this x to be the same like e raised to the power the natural log of x. Friends, let me show you why this statement is true, okay? Let me show you why this statement is true. Let's look at the graph of natural log of x and the graph of e raised to the power x. Let's have the vertical axis, which we can call that y. Horizontal axis, we can call that x. Now, friends, these are the points 1, 1, because the graph of natural log of x and e raised to the power x are going to touch. The graph of e raised to the power x will touch the y-axis when x is 0, and it will touch the graph of natural log of x will touch the x-axis when y is 0. Good. So, friends, in that light now, this is how the graph of e raised to the power x looks like. Okay, that's it. Graph of e raised to the power x. That's what we have. Then, friends, you see that if we reflect e raised to the power x completely, okay, if we just reflect it about the line x equals to y, okay, or if we reflect it in such a way that it lands on this positive x-axis, we'll see that we are going to get the graph of y equal to natural log of x, which is what we have here, y equal to ln x. So friends, you can see that the e raised to the power x and the ln x are just mirror images of each other, right? Because if you fold e raised to the power x, it will fit in directly into where you have natural log of x, and vice versa. If you fold the graph of natural log of x, it will fall exactly on where you have the graph of e to the power x. So friends, by so doing, we can go ahead to draw a mirror line which is going to cut the Cartesian plane into two equal halves, okay, and that's the line x equal to y. Great. So friends, hope it was understood. So by so doing now guys, I'm sure you now understand why x can be written as e raised to the power natural log of x, because the e and the natural log of x, the e and the natural log, they can cancel, and we just have our result to be x. That therefore implies, guys, we can replace this our x in yellow by simply e raised to the power natural log of x. That therefore implies we are going to have the integral of x raised to the power x over ln x, which is going to translate into just the integral of our x is simply what, guys? It is simply e raised to the power natural log of x, right? Then the power in blue, we have x over natural log of x. But friends, we start the natural log of x can cancel the natural log of x outside, okay? These two natural log of x in yellow, they can cancel. Don't mind us how they are, guys, okay? You're simply multiplying the exponent of something with another which is outside, so they can simply multiply themselves out conveniently, and you start this natural log of x will be at the top, this y on stairs at the bottom. They can cancel. So in essence, guys, when these two guys cancel, we are just going to have now but the integral of e raised to the power x. This is the x in white, which is here, the x. As you all know, guys, this is very cheap, right? This is childish. Even the class 1 child can tell you the answer. This just gives us the same e raised to the power x plus c. Great. Integrating e raised to the power x, guys, simply gives you e raised to the power x, and differentiating it simply gives you e raised to the power x. Great. So that's it for this video, guys. That's it. I hope you enjoyed the video. Please put in the comment section down below if there's something you think about this question. If you didn't understand anything, guys, please add it as a comment. I'm going to reply to it as soon as possible. And please don't forget to like the video. Please like the video so that it's going to help others locate our contents. Thank you so much, and have a blessed day.